Welcome to the I Can't Sleep podcast, where I help you drift off one fact at a time. I'm your host, Benjamin Boster, and today's episode is about 3D printing. 3D printing, also called additive manufacturing, is the construction of a three-dimensional object from a CAD model or a digital 3D model. It can be done in a variety of processes in which material is deposited, joined, or solidified under computer control, with the material being added together, e.g. plastics, liquids, or powder grains being fused, typically layer by layer. In the 1980s, 3D printing techniques were considered suitable only for the production of functional or aesthetic prototypes, and a more appropriate term for it at the time was rapid prototyping. As of 2019, the precision, repeatability, and material range of 3D printing have increased to the point that some 3D printing processes are considered viable as an industrial production technology. In this context, the term additive manufacturing can be used synonymously with 3D printing. One of the key advantages of 3D printing is the ability to produce very complex shapes or geometries that would be otherwise infeasible to construct by hand, including hollow parts or parts with internal truss structures to reduce weight while creating less material waste. Fused deposition modeling, FDM, which uses a continuous filament of a thermoplastic material, is the most common 3D printing process in use as of 2020. The umbrella term additive manufacturing, AM, gained popularity in the 2000s, inspired by the theme of material being added together in any of various ways. In contrast, the term subtractive manufacturing appeared as a retronym for the large family of machining processes with material removal as their common process. The term 3D printing still referred only to the polymer technologies in most minds, and the term AM was more likely to be used in metalworking and end-use part production contexts than among polymer, inkjet, or stereolithography enthusiasts. By the early 2010s, the terms 3D printing and additive manufacturing evolved senses in which they were alternate umbrella terms for additive technologies, one being used in popular language by consumer maker communities and the media, and the other used more formally by industrial end-use part producers, machine manufacturers, and global technical standards organizations. Until recently, the term 3D printing has been associated with machines low in price or capability. 3D printing and additive manufacturing reflect that the technologies share the theme of material addition, or joining, throughout a 3D work envelope under automated control. Peter Zielinski, the editor-in-chief of Additive Manufacturing magazine, pointed out in 2017 that the terms are still often synonymous in casual usage. But some manufacturing industry experts are trying to make a distinction whereby additive manufacturing comprises 3D printing plus other technologies, or other aspects of a manufacturing process. Other terms that have been used as synonyms or hypernyms have included desktop manufacturing, rapid manufacturing, as the logical production-level successor to rapid prototyping, and on-demand manufacturing, which echoes on-demand printing in the 2D sense of printing. The fact that the application of the adjectives rapid and on-demand to the noun manufacturing was novel in the 2000s reveals the long prevailing mental model of the previous industrial era, during which almost all production manufacturing had involved long lead times for laborious tooling development. Today, the term subtractive has not replaced the term machining, instead complementing it when a term that covers any removal method is needed. Agile tooling is the use of modular means to design tooling that is produced by additive manufacturing or 3D printing methods to enable quick prototyping and responses to tooling and fixture needs. Agile tooling uses a cost-effective and high-quality method to quickly respond to customer and market needs, and it can be used in hydroforming, stamping, injection molding, and other manufacturing processes. The general concept of and procedure to be used in 3D printing was first described by Murray Leinster in his 1945 short story, Things Pass By. But this constructor is both efficient and flexible. I feed magnotronic plastics, the stuff they make houses and ships of nowadays, into this moving arm. It makes drawings in the air. Following drawings, it scans with photocells. But plastic comes out of the end of the drawing arm and hardens as it comes, following drawings only. It was also described by Raymond F. Jones in his story, Tools of the Trade, published in the November 1950 issue of Astounding Science Fiction magazine. He referred to it as a molecular spray in that story. In 1971, Johannes F. Gottwald patented the liquid metal recorder, U.S. Patent 3596285A, a continuous inkjet metal material device to form a removable metal fabrication on a reusable surface for immediate use, or salvaged for printing again by remelting. This appears to be the first patent describing 3D printing with rapid prototyping and controlled on-demand manufacturing of patterns. The patent states, "As used herein, the term printing is not intended in a limited sense, but includes writing or other symbols, character or pattern formation with an ink. The term ink as used is intended to include not only dye or pigment-containing materials, but any flowable substance or composition suited for application to the surface for forming symbols, characters, or patterns of intelligence by marking. The preferred ink is of a hot melt type. The range of commercially available ink compositions which could meet the requirements of the invention are not known at the present time. However, satisfactory printing according to the invention has been achieved with a conductive metal alloy as ink. But in terms of material requirements for such large and continuous displays, if consumed at theretofore known rates, but increased in proportion to increase in size, the high cost would severely limit any widespread enjoyment of a process or apparatus satisfying the foregoing objects. It is therefore an additional object of the invention to minimize use to materials in a process of the indicated class. It is a further object of the invention that materials employed in such a process be salvaged for reuse. According to another aspect of the invention, a combination for writing and the like, comprises a carrier for displaying an intelligence pattern and an arrangement for removing the pattern from the carrier. In 1974, David E. H. Jones laid out the concept of 3D printing in his regular column Ariadne in the journal New Scientist. Early additive manufacturing equipment and materials were developed in the 1980s. In April 1980, Hideo Kodama of Nagoya Municipal Industrial Research Institute invented two additive methods for fabricating three-dimensional plastic models with photo-hardening thermoset polymer, where the UV exposure area is controlled by a mask pattern or a scanning fiber transmitter. He filed a patent for this XYZ plotter, which was published on the 10th of November 1981. His research results as journal papers were published in April and November 1981. However, there was no reaction to the series of his publications. His device was not highly evaluated in the laboratory, and his boss did not show any interest. His research budget was just 60,000 yen, or $545 a year. Acquiring the patent rights for the XYZ plotter was abandoned, and the project was terminated. A U.S. 4322756 patent, method of fabricating articles by sequential deposition, granted on the 6th of April 1982 to Raytheon Technologies Corp., describes using hundreds or thousands of layers of powdered metal and a laser energy source, and represents an early reference to forming layers and the fabrication of articles on a substrate. On the 2nd of July 1984, American entrepreneur Bill Masters filed a patent for his computer automated manufacturing process and system, US 4665492. This filing is on record at the USPTO as the first 3D printing patent in history. It was the first of 3 patents belonging to Masters that laid the foundation for the 3D printing systems used today. On the 16th of July 1984, Alain Lemerté, Olivier David, and Jean-Claude André filed their patent for the stereolithography process. The application of the French inventors was abandoned by the French General Electric Company and Silas, the Laser Consortium. The claimed reason was for lack of business perspective. In 1983, Robert Howard started RH Research, later named Howtech Inc., in February 1984, to develop a color inkjet 2D printer, Pixelmaster, commercialized in 1986 using thermoplastic hot melt plastic ink. A team was put together, 6 members from Exxon Office Systems, Danbury Systems Division, an inkjet printer startup, and some members of Howtech Inc. Group, who became popular figures in the 3D printing industry. One Howtech member, Richard Helinsky, patent US 5136515A, method and means for constructing three-dimensional articles by particle deposition, application November 7, 1989, granted August 4, 1992, formed a New Hampshire company, CADcast Inc., named later changed to Visual Impact Corporation, VIC, on August 22, 1991. A prototype of the VIC 3D printer for this company is available with a video presentation showing a 3D model printed with a single nozzle inkjet. Another employee, Herbert Manhattan, formed a New Hampshire company, HM Research, in 1991 and introduced the Howtech ink inkjet technology and thermoplastic materials to Royden Sanders of SDI and Bill Masters of Ballistic Particle Manufacturing, BPM, where he worked for a number of years. Both BPM 3D printers and SPI 3D printers use Howtech ink-style inkjets and Howtech ink-style materials. Royden Sanders licensed the Hellingse patent prior to manufacturing the Model Maker 6 Pro at Sanders Prototype Inc. SPI in 1993. James K. McMahon, who was hired by Howtech Inc. to help develop the inkjet, later worked at Sanders Prototype and now operates Layer Grown Model Technology, a 3D service provider specializing in Howtech single nozzle inkjet and SDI printer support. James K. McMahon worked with Stephen Zoltan, 1972 drop-on-demand inkjet inventor, at Exxon, and has a patent in 1978 that expanded the understanding of the single nozzle design inkjets, alpha jets, and helped perfect the Howtech ink hot melt inkjets. This Howtech hot metal thermoplastic technology is popular with metal investment casting, especially in the 3D printing jewelry industry. Sanders' SDI first Model Maker 6 Pro customer was Hitchner Corporation's Metal Casting Technology, Inc. in Milford, New Hampshire, a mile from the SDI facility, in late 1993 to 1995, casting golf clubs and auto engine parts. On the 8th of August 1984, a patent, US 4575330, assigned to UVP Inc., later assigned to Chuck Hull of 3D Systems Corporation, was filed, with his own patent for a stereolithography fabrication system, in which individual laminae or layers are added by curing photopolymers with impinging radiation, particle bombardment, chemical reaction, or just ultraviolet light lasers. Hull defined the process as a system for generating three-dimensional objects by creating a cross-sectional pattern of the object to be formed. Hull's contribution was the STL file format and the digital slicing and infill strategies common to many processes today. In 1986, Charles Chuck Hull was granted a patent for this system, and his company, 3D Systems Corporation, was formed, and it released the first commercial 3D printer, the SLA-1, later in 1987 or 1988. The technology used by most 3D printers to date, especially hobbyist and consumer-oriented models, is fused deposition modeling, a special application of plastic extrusion developed in 1988 by S. Scott Crump and commercialized by his company Stratasys, which marketed its first FDM machine in 1992. Owning a 3D printer in the 1980s cost upwards of $380,000. Or $650,000 in 2016 dollars. AM processes for metal sintering or melting, such as selective laser sintering, direct metal laser sintering, and selective laser melting, usually went by their own individual names in the 1980s and 1990s. At the time, all metalworking was done by processes that are now called non-additive: casting, fabrication, stamping, and machining. Although plenty of automation was applied to those technologies, such as by robot welding and CNC, the idea of a tool or head moving through a 3D work envelope, transforming a mass of raw material into a desired shape with a tool path, was associated in metalworking only with processes that removed metal rather than adding it, such as CNC milling, CNC EDM, and many others. However, the automated techniques that added metal, which would later be called additive manufacturing, were beginning to challenge that assumption. By the mid-1990s, new techniques for material deposition were developed at Stanford and Carnegie Mellon University, including microcasting and sprayed materials. Sacrificial and support materials had also become more common, enabling new object geometries. The term 3D printing originally referred to a powder bed process employing standard and custom inkjet printheads, developed at MIT by Emanuel Sachs in 1993, and commercialized by Soligen Technologies, Extrude Hone Corporation, and Z Corporation. The year 1993 also saw the start of an inkjet 3D printer company, initially named Sanders Prototype Inc., and later named SolidScape, introducing a high-precision polymer jet fabrication system with soluble support structures, categorized as a dot-on-dot technique. In 1995, the Fraunhofer Society developed the selective laser melting process. In the early 2000s, 3D printers were still largely being used just in the manufacturing and research industries, as the technology was still relatively young and was too expensive for most consumers to be able to get their hands on. The 2000s was when larger-scale use of the technology began being seen in industry, most often in the architecture and medical industries, though it was typically used for low-accuracy modeling and testing, rather than the production of common manufactured goods or heavy prototyping. In 2005, users began to design and distribute plans for 3D printers that could print around 70% of their own parts, the original plans of which were designed by Adrian Bowyer at the University of Bath in 2004. The name of the project being RepRap, Replicating Rapid Prototyper. Similarly, in 2006, the Fab at Home project was started by Evan Malone and Hod Libson, another project whose purpose was to design a low-cost and open-source fabrication system that users could develop on their own and post feedback on, making the project very collaborative. Much of the software for 3D printing available to the public at the time was open source, and as such was quickly distributed and improved upon by many individual users. In 2009, the fused deposition modeling FDM printing process patents expired. This opened the door for a new wave of startup companies, many of which were established by major contributors of these open-source initiatives, with the goal of many of them being to start developing commercial FDM 3D printers that were more accessible to the general public. As the various additive processes matured, it became clear that soon metal removal would no longer be the only metalworking process done through a tool or head moving through a 3D work envelope, transforming a mass of raw material into a desired shape layer by layer. The 2010s were the first decade in which metal end-use parts, such as engine brackets and large nuts, would be grown, either before or instead of machining, in job production, rather than obligately being machined from bar stock or plate. It is still the case that casting, fabrication, stamping, and machining are more prevalent than additive manufacturing and metalworking, but AM is now beginning to make significant inroads, and with the advantages of design for additive manufacturing, it is clear to engineers that much more is to come. One place that AM is making a significant inroad is in the aviation industry. With nearly 3.8 billion air travelers in 2016, the demand for fuel-efficient and easily produced jet engines has never been higher. The large OEMs, original equipment manufacturers like Pratt & Whitney, PW, and General Electric, GE, this means looking towards AM as a way to reduce cost, reduce the number of non-conforming parts, reduce weight in the engines to increase fuel efficiency, and find new, highly complex shapes that would not be feasible with the antiquated manufacturing methods. One example of AM integration with aerospace was in 2016, when Airbus delivered the first of GE's LEAP engines. This engine has integrated 3D printed fuel nozzles, reducing parts from 20 to 1, a 25% weight reduction, and reduced assembly times. A fuel nozzle is the perfect inroad for additive manufacturing in a jet engine, since it allows for optimized design of the complex internals, and it is a low-stress, non-rotating part. Similarly, in 2015, PW delivered their first AM parts in the Pure Power PW1500G to Bombardier. Sticking to low-stress, non-rotating parts, PW selected the compressor stators and sink ring brackets to roll out this new manufacturing technology for the first time. While AM is still playing a small role in the total number of parts in the jet engine manufacturing process, the return on investment can already be seen by the reduction in parts, the rapid production capabilities, and the optimized design in terms of performance and cost. As technology matured, several authors began to speculate that 3D printing should aid in sustainable development in the developing world. In 2012, Philibot developed a system for closing the loop with plastic that allows for any FDM or FFF 3D printer to be able to print with a wider range of plastics. In 2014, Benjamin S. Cook and Manos M. Tentsiris demonstrated the first multi-material vertically integrated printed electronics additive manufacturing platform, Viper, which enabled 3D printing of functional electronics operating up to 40 gigahertz. As the price of printers started to drop, people interested in this technology had more access and freedom to make what they wanted. As of 2014, the price for commercial printers was still high, with the cost being over $2,000. The term 3D printing originally referred to a process that deposits a binder material onto a powder bed, with inkjet printer heads layer by layer. More recently, the popular vernacular has started using the term to encompass a wider variety of additive manufacturing techniques, such as electron beam additive manufacturing and selective laser melting. The United States and global technical standards use the official term additive manufacturing for this broader sense. The most commonly used 3D printing process, 46% as of 2018, is a material extrusion technique called fused deposition modeling, or FDM. While FDM technology was invented after the other two most popular technologies, stereolithography, SLA, and selective lasering sintering, SLS, FDM is typically the most inexpensive of the three by a large margin, which lends to the popularity of the process. As of 2020, 3D printers have reached the level of quality and price that allows most people to enter the world of 3D printing. In 2020, decent quality printers can be found for less than $200 for entry-level machines. These more affordable printers are usually fused deposition modeling FDM printers. In November 2021, a British patient named Steve Verse received the world's first fully 3D printed prosthetic eye from the Moorfields Eye Hospital in London. In April 2024, the world's largest 3D printer, the Factory of the Future 1.0, was unveiled at the University of Maine. It is able to make objects 96 feet long. In 2024, researchers used machine learning to improve the construction of synthetic bone and set a record for shock absorption. In July 2024, researchers published a paper in Advanced Materials Technologies describing the development of artificial blood vessels using 3D printing technology, which are as strong and durable as natural blood vessels. The process involved using a rotating spindle integrated into a 3D printer to create grafts from a water-based gel, which were then coated in biodegradable polyester molecules. Additive manufacturing, or 3D printing, has rapidly gained importance in the field of engineering due to its many benefits. The vision of 3D printing is design freedom, individualization, decentralization, and executing processes that were previously impossible through alternative methods. Some of these benefits include enabling faster prototyping, reducing manufacturing costs, increasing product customization, and improving product quality. Furthermore, the capabilities of 3D printing have extended beyond traditional manufacturing, like lightweight construction or repair and maintenance, with applications in prosthetics, bioprinting, food industry, rocket building, design and art, and renewable energy systems. 3D printing technology can be used to produce battery energy storage systems, which are essential for sustainable energy generation and distribution. Another benefit of 3D printing is the technology's ability to produce complex geometries with high precision and accuracy. This is particularly relevant in the field of microwave engineering, where 3D printing can be used to produce components with unique properties that are difficult to achieve using traditional manufacturing methods. Additive manufacturing processes generate minimal waste by adding material only where needed, unlike traditional methods that cut away excess material. This reduces both material costs and environmental impact. This reduction in waste also lowers energy consumption for material production and disposal, contributing to a smaller carbon footprint.